Okay, next example, example 3. We're going to find the derivative for xy equals cotangent of xy. All right, on the left we've got a product rule, so it's going to be the first times the derivative of the second, which is just dy dx, plus the second times the derivative of the first. Okay, that's the left side. Now let's go to the right side. The derivative of cotangent of x with an angle in there. So the derivative of cotangent x would be negative cosecant squared the angle. Now times the derivative of the angle. Well, the derivative of the angle is just xy, which is pretty much what we just did on the left side, where it's the first times the derivative of the second plus the second times the derivative of the first. So this is kind of a little chain rule going on right here on the right side total. Okay, canceling off dx dx's, because not getting a whole lot from there. So we get x dy dx plus y is equal to a negative cosecant squared xy times x dy dx plus y. Okay, and then from there we're just going to keep doing some more math just so that we can focus on just getting the dy dx's all by themselves. So we have x dy dx plus y is equal to negative cosecant squared xy times x dy dx minus, I'll just go and write it as y, cosecant squared xy. Okay, let's maybe move this huge term right here over to the left and factor out the dy dx. And let's move this y over to the right side since it has nothing to do with dy dx. Okay, so we'll get x plus cosecant squared xy times x, all of that dy dx is equal to a negative y minus y cosecant squared xy. And last but not least, just getting dy dx by itself. So dividing off that bracket there on the left side, I don't know if you want to factor out the negative. You can write it as y plus y cosecant squared xy divided by, and then down there, let's write it as x plus, I'll write it as x cosecant squared xy. All right, that right there represents the derivative. And again, the derivative both has an x and y variable in it, so for us to further go on and say, hey, what's the slope for this function, they have to give us a specific coordinate, not just part of a coordinate. Okay, example 4. We want to find the derivative for a very large function, r minus 2 theta, 2 squares of theta, and then the other side with 3/2 theta to the 2/3, 4/3 theta to the 3/4. All right, we're seeing every inside exponent and everything on the right side. Let's look on that left side for just 1 second. So I read it as r minus 2, and then it should be theta to the 1/2 power is equal to 3/2 theta to the 2/3 plus 4/3 theta to the 3/4. Okay, let's go back. They're wanting us to find dr d theta. So we're taking the derivative of r with respect to theta. Okay. Getting started then. I'm going to go to the new version, quote unquote, that I wrote. So the derivative of r would be 1 dr d theta. We're taking the derivative of r with respect to theta. Okay, and then right here we'll go minus. Let's bring down the exponent. So 1/2 of 2 is 1. So it'd be 1 theta to the negative 1/2 d theta is equal to, let's just write it like this, 3/2 times 2/3 theta to the negative 1/3 d theta plus 4/3 times 3/4 theta to the negative 1/4 d theta. Then going through and canceling, we don't really need the d thetas, but it's nice to have practice in there when you're writing these down. Okay, so we have dr d theta, not equals, I don't want to get too far ahead of ourselves just real quick. So minus theta to the negative 1/2 is equal to, looks like everything cancels there, so it'd be theta to the negative 1/3. Everything cancels there, so plus theta to the negative 1/4. Okay, almost finished. dr d theta is equal to theta to the negative 1/3 plus theta to the negative 1/4 minus, or plus, by the time I move it over, theta to the negative 1/2. All right. This time the derivative is all in terms of just our independent variable, which is theta. And so if they wanted us to find it at a specific point, they would just have to give us, hey, find the derivative when theta equals 4 or something like that. And then we can go from there. Okay. For y squared minus 2x equals 1 minus 2y, we're going to find both the first derivative and the second derivative. Okay, so let's do the first derivative first. Let's find dy dx. Starting out, it'll be 2y dy dx. And maybe, hopefully, is it okay if I start dropping some of these now? So the derivative of 2x, of a minus 2x, would be a negative 2 dx dx. I'm just not going to worry about writing that now, if that's okay. The derivative of 1 is 0, and the derivative of negative 2y would be a negative 2 dy dx. Okay, so let's move, looks like that term over, so we can focus on just our dy dx's and factor that out. So it'll be 2y plus 2 dy dx is equal to 2. She'll take 2 seconds and double check, make sure you agree. And then dy dx is equal to 2 over 2y plus 2, and let's go ahead and fully reduce that to make our life as much easier as possible on us when we go to the next part. Okay, so that's originally what our function is. Now if we go in there and find the second derivative. Okay, to get started with that one then, we'll write it as, let's see, the second derivative, d squared y over dx squared. Okay, here are the steps. I guess if you don't want to do the quotient rule, we can come over here and just write that as y plus 1 to the negative 1 if you want to do it like that. It might be a little easier or just different. But we have dy dx, okay, is equal to then y plus 1 to the negative 1. So when we go in there and take the second derivative, we're taking the derivative on the left. So d squared y over dx squared is going to equal negative 1 times your base to your subtract 1, and then times the derivative of the base, which is dy dx. Okay, so d squared y over dx squared is going to equal a negative 1 over y plus 1 squared, and then times dy dx. Now we don't want to stop right there because we want to get all of dy dx in terms of just x's and y's. We don't want to have this term over here. Okay, and because we can easily solve for it, all we have to do is go back over here to what it actually equals. Okay, well, so d squared y, the second derivative, is equal to negative 1 over y plus 1 squared, and then dy dx is 1 over y plus 1. So combining this all together so we can get our very final answer, we can just write it as negative 1 over y plus 1, all that cubed. And there is your final answer. And expect to do that. Expect that when you go to find the second derivative, that's going to be in the terms of involving the first derivative, and you're going to go make that substitution in it. So that's why it's kind of nice. We're going to find definitely the first derivative first, and then from there go find the second derivative. Okay? And plug in the pieces together. And I guess if we found the third derivative, and third derivative would be involved both the second derivative and the first derivative, so you'd be plugging in and plugging in all along the chain as you go.